Session with Marco Linton, who's going to tell us about the coherence of one-relator groups.
Thank you. Yeah, thanks for organizing this wonderful conference and for inviting me. So yeah, as my title says, I'm going to talk about the coherence of one-relator groups, and this is all joint work with Andrei Jaikin-Zapirain. So first, I should define terms in my title. So I'm sure you've seen this before, but let's write it out. So group G is coherent. Underline the definition. If every finitely generated, I'm going to abbreviate this by FG because you'll see this a lot, is every finitely generated subgroup is finitely presented. Okay, and this is F dot P. Okay, so this talk is going to be all about subgroups. And geometry maybe is debatable, but we'll see. Okay, so, and the second thing is one-relator groups. Okay, I guess this maybe is self-explanatory. Presentation, one relation. But I'm going to talk about, more specifically, this conjecture or Baumslag, 74. All one-relator groups are coherent. Right, so before I get started with the talk, maybe we should do some examples. Does anybody know what the first example of a finitely presented incoherent group was? Not quite. Almost.
F2 cross B is 1, 2.
Exactly. Yeah. Okay, you know your stuff. All right. So the record. First finitely presented incoherent group, F2 cross BS 1, 2. Okay, so what's BS12? It's the Baumslag solid tile group. It has one relation. We write this out. So the free group generated by P and Q. And this guy is going to have generators A and B. And A is going to conjugate B to a power of itself. So this example is due to Baumslag and Neumann from 59. Okay, so this is before Pigman's embedding theorem, which is maybe a cheap way of finding incoherent finitely presented groups. And they do this very explicitly. They don't just say, you know, you have some fancy machinery, maybe some Morse theory, and you know you've got some finitely generated subgroup which is not finitely presented. They just do this. They just take the presentation. They just work out the details. Say there's infinitely many relations to present this subgroup. And maybe I'll give. Yeah, if you get bored in my talk, you can figure this out. So the subgroup they give is generated by B, A, Q, and P. So this is isomorphic to the following. So you have the normal closure of P in a copy of F2. And this all commutes with subgroup isomorphic to the dyadic integers and semi-direct product with what is it? AQ, that's it. Okay, this is not finally presented. So exercise is showing this and that it's not finally presented. Okay, that's the last incoherent group you're going to see in this talk. From now on, it's all going to be nice, coherent things. So yeah, now examples of coherent groups. So the first examples, which you might think of, I'm going to label them as 0 because they're kind of, well, they're a level below coherence even. So finite groups. So not only are they coherent, but all their subgroups are finitely generated and a finite multiplication table. So just as simple as possible if you're an infinite group theorist. And another similar example, abelian groups. Again, if you say finitely generated abelian groups, all their subgroups are finitely generated. That's why it's 0. Okay, so the first set of examples, which maybe are not immediate, but known for many, many, many years, free groups. So free group is fundamental group of graph. Covering space theory just tells you all their subgroups are free groups, which is one of the proofs that I don't know, that I really liked when I was young undergraduate starting to get into geometric group theory. And similarly, also surface groups, similar, maybe more involved proof. So more examples. Okay, now we get to something which is more of a more recent theorem. Say recent, still 50 years old. So if you take a free product amalgamation over Z, where G and H are free, this is also going to be coherent. So this is proved by Carras and Solitar in 1970. This is probably the first result, at least the first result that I'm aware of, where coherence is really sort of studied as a property in itself. And they claim, and they say in this paper that they answer a question of Baumslag. So Baumslag was already thinking about coherence before this. Yes. Yes, but you might not like it. It was first defined for rings, like 61, Bourbaki. It defined coherent ring as one where all its finally generated submodules, finally generated rings, ideals are finally presented. Yeah, and that was, a while ago. And of course, they spelled it like this. Yeah. But the first time the word coherence was used for groups was actually, in the same sort of book where Baumslag's conjecture was published, but not used by Baumslag, used by Serre. Yeah, Serre defined it first for groups, and he also conjectured that certain linear groups people are interested in knowing whether they're incoherent or not, or incoherent. Yeah. Okay, so these are the first non-surface one-relator groups known to be coherent. Another results, three manifold groups. So this is due to Scott and independently Shailen. This is 73. Okay, again, this is also before coherence was defined, but yeah, clearly it was studied before. And final example is free bicyclic groups. This is a result of Fein Handel. And here the free group is not necessarily finally generated. It's just the free group. Okay, are there any coherent groups I've missed out? Okay, well, the purpose of this talk is to add a new class of coherent groups to this list, which I've seen about 1 million times. So this is our main theorem. One-related groups are all coherent. Okay, so this is the theorem. The rest of the talk is just going to be basically me discussing the proof, and it's going to be a sort of recipe for proving coherence of groups. Okay, so you too can prove coherence. There are going to be three sort of main steps, three ingredients. Very simple recipe, if you're talking about cooking. So what's the first step? So, okay. So step one. This is something that was possibly initiated by Danny Wise around 20 years ago. So was definitely initiated, definitely. Okay, maybe the broad idea, yes, definitely initiated by Danny Wise. Okay, so study subgroups via immersions of two complexes. Okay, well, yeah, so in the case of free groups and surface groups, the proof of coherence just, you can look at covering spaces and they will have to be of a very nice form. So you can sort of understand the subgroups in that sense by studying immersions of things. Okay, and the idea is to sort of generalize that to a suitable class of two complexes. I mean, all two complexes is quite broad, so we have to restrict our attention to certain subclass, which was definitely introduced by Danny Wise in And I'll define that in a second, but first I'll say what I mean by immersions of two complexes. So, okay, two complex X, X will always be two complex, consists of nothing other than like a one skeleton. You can think of this as like a presentation complex of your favorite group. So maybe it's just the one skeleton is a rose, okay, together with an immersion of cycles. So this is just a circle, and an immersion is a locally injected map. Okay, so this is just what I'm going to consider as a two complex. I mean, formally, it's just a graph and immersions of circles. And if you want to take the topological realization, you just add a disk along this immersion. And in particular, I'm not considering two complexes where the boundary maps are just mapped to points. They have to be nice immersions of circles. Okay, so that's what two complexes are. Then, so let's put this by Sx. Then an immersion of two complexes will be, well, at the level of graphs, it's just an immersion of graphs. Let's draw some random graph like this. This is Y, okay? And this will also have two cells, or maybe not. So this is just a bunch of circles, again, which immerse. Maybe there's more, Sy. And there will also be an immersion over here of these circles into these circles here, okay? And well, this is a true immersion. Really, you want this to be an isomorphism on each component of each circle. So this is how I want to think about immersions of two complexes. Now, the key definition is that of non-positive immersions. It does what it says on the tin. So a two complex has non-positive immersions. Here we go. And I'll often abbreviate it by NPI, just to, because I'll write it down a lot. If every compact two complex, okay, connected two complex, immersing, so Y immersing into X has, well, either you want the Euler characteristic to be non-positive, or, well, I mean, if you took a point, then the Euler characteristic is not going to be non-positive. So we want to eliminate something like that, or Y is homotopy equivalent to a point. And there are different variations of this definition, but this is perhaps the most, well, maybe the quickest to state. Okay. And it turns out you get some nice properties just from this definition. So Y showed that if X has non-positive immersions, then firstly X is aspherical. Okay. And secondly, fundamental group of X is locally indicable. 20. I think this is all known way before then, but I think this is when it was published. Okay. Now, obviously, I'm defining this for a reason. So, and the reason is the following theorem, which is a very nice, well, really like the proof. Very nice result. And this is due independently to Helfer and Wise and Lauder and Wilton. Okay, let's Wise and Lauder Wilton. And this, yeah, around 17 maybe it was published. And the result is if X has 1, 2 cell, 1, 2 cell, so like presentation complex of a one-relator group. And okay, and fundamental group is torsion free. There's also a version when there's torsion, but I don't want to get into that story too much. So torsion free, then X has non-positive immersions. Again, how should you think about this result? Okay, we have this very convenient picture of a presentation complex of a one-relator group. And what does this result say? It says, okay, for every immersion of a graph, which is the one skeleton of our like theoretical two complex into the one skeleton of X, there's going to be at most minus order characteristic of this guy many two cells which immerse over here, making this diagram commute. So what does that mean? Well, we have two maps of graphs, and this has to somehow be sitting inside the pullback of these two maps of graphs. So proving this was a matter of looking at graphs and pullbacks of graphs, and it came out of proving the rank 1 Hahn-Neumann conjecture. Oh yeah, that's it. Thanks. You just have it. There's hyphens everywhere. There's going to be three hyphens later for two people. That'll be exciting. Okay, Hahn-Neumann conjecture, which states, so this was conjectured by Wise right when he started working on this stuff. And so what does it say? It says, well, if you have, let's say, a finely generated subgroup or a free group, and you have some elements, which is not a proper power, then the sum, the sum of the double coset representatives of this rank. So you sum over all the intersections of H with conjugates of W. So this has to be bounded above by the rank of H. This is like a cyclic version of the Hahn-Neumann conjecture, which sort of forgets about the cyclic subgroups because you take reduced ranks. And here it's really just the ranks of the subgroups. So yeah, these authors proved essentially this conjecture. There's something I'm not saying here, but okay. And from here you look at the graphs and you can get non-positive immersions. Okay, and when this theorem was proved, naturally there was some amazing progress on coherence, which I just want to briefly mention. But if you want to learn more, you should talk to Lars or Henry. So let's see. Yeah, okay. So if here I'm assuming X has 1, 2 cell. So if fundamental group of X has torsion, or so this was also proved by Wise, or X has negative emergence, fundamental group of X is coherent. But not only that, you also have a bunch of other really nice strong properties on the subgroups. So somehow looking at something slightly more restrictive really gets you like a lot of extra nice properties, subgroup. And these properties are all false for general non-positive immersions. So now the Linton. Sorry, could you? Okay, so yeah, I'm being a little bit vague. So here X has 1, 2 cell, but here it's more, the result is more general. It's not just for two complexes with a single 2 cell. So it's also for general 2 complexes which have negative immersions, or well, not uniform negative immersions. But for one-relator complexes, it really is negative immersions. So exactly what you're thinking in your mind. You just change the inequality and maybe add the hypothesis that you can add circles as well, which have 0 order characteristic. So now the Wilton and Wise. Okay. So this is the first part of the recipe. Understand non-positive immersions. Show your favorite groups have non-positive immersions. Now, step 2, or ingredient number 2, is homology. Okay. So now we're going to move a little bit away from classic coherence. Well, a group. So yeah, find what the group of type FP2 is. So group G has type FP2. over Z. If the trivial module has a projective resolution or a partial projective resolution, all the projectives are finally generated. Okay, write that down. So, yeah, what do I say? Okay, so yeah, if you have some resolution with PI projective and finally generated ZG modules. Okay. Well, yeah. Why am I doing this? Why am I switching up from coherence to homology? Well, it turns out that having non-positive mergence is really useful for computing homology. Your two complexes are aspherical, so the homology of your group is just, you get a free resolution of this form just from the two complex. So we're going to use this. Right. Here's a new definition. Okay, and another one is G is homologically coherent. If you can guess this, every finally generated subgroup has type FP2 over Z. Okay. Now, I don't think there are any known examples of groups which are incoherent but homologically coherent. I'd be very interested to know that. So, example, all the groups of type FP2 over Z, but not which are not finally presented, which arise as subgroups of right-angle Artin groups, they're all incoherent. And also, I wanted to emphasize that they do exist. There are finally generated subgroups, not finally presented, but have type FP2 over Z.
A question.
Yeah.
Probably explain your terms about projective resolution. Like, so why does coherent like homological coherence?
Oh no, coherence does not imply homological coherence. No. Sorry.
Yeah.
Sorry. No. Yeah. Sorry. I thought you said the other way around. Yeah. Coherence implies homological coherence. Yeah. Well, because if you are coherent, or take a finally generated subgroup H, which is finally presented, then you can take a, what does it mean? You can take a resolution by, so ZH to the N, where N is the number of generators, to Z. And then the kernel here is going to be and you can take a ZH to the M, where M is the number of relators. And then you might carry on like this, but this is going to be finite. Yeah, you take, okay, maybe it's easy to just take a classifying space. It's going to have finite 2 skeleton. Yeah, has finite 2 skeleton, and that gives you this free resolution. Any other questions? Okay, but maybe, so it's unknown whether there exists homologically coherent but not coherent groups, but there is this really nice result of Gersten, at least for hyperbolic groups. So if G is hyperbolic and has cohomological dimension at most 2, then they're equivalents. So homologically coherent for G is actually equivalent to coherence. What he shows is something much stronger. It shows that all the subgroups of type FP2 over Z are actually hyperbolic. But yeah, this is one application. Okay. Now, next, what's the criterion? Step 2. Result, again with Jaikin and I this year. So we showed that if X has non-positive emergence, then pi1 of X is homologically coherent. So it's really hard to get at finite presentations. But if you look at homology, it's a little bit simpler. I just want to outline a little bit how we prove this result.
X here is
2 complex with non-positive emergence. Yeah, that's it. Yeah. No other hypothesis. Thank you. If I say anything unclear, please do ask me so I can clarify. Right. Okay. So the idea. Well, firstly, here's a criterion, useful criterion, which may not seem very useful on the face of it, but I'll explain why it is useful. So, useful criterion. So if G, so G is just a finitely generated group, okay, and cohomological dimension of G is at most 2. I'm always going to be assuming this. It's hard to think of higher dimensional things, so just 2-dimensional. And here's the extra, maybe surprising hypothesis. So we want our group ring to embed into a division ring. Okay, so where D, so D is a division ring. I'm sorry. Okay. Well, then what? Then there's the following way to tell if your subgroup or group is of type FP2 of Z. So G has type FP2 of Z, if and only if the dimension, so D dimension, so it's a division ring, so you can think of it essentially as a, it's essentially a field, but it's non-commutative. So modules over a field of X spaces. So you can, you have a well-defined dimension. And so what's the criterion? Well, if the dimension of the second homology group of G with coefficients in D is finite. So here the action on D is just given by this embedding of a group ring. Yeah, on the face of it, maybe not obvious why it's useful. You just have an embedding. You don't really know what this embedding is or how ZG acts on D or anything like that. But now I'll explain why it's useful in our context. But firstly, I should mention a few results. So, because I guess it's also not obvious why a group ring should embed into a division ring. So torsion-free. Sorry? Yes. Yeah. Because I mean, that one way to proving coherence, or a group is not of type FP2 over Z would be to show that its second normal homology group is infinitely generated. But this is not always the case when you're not. Yeah, this is not always the case. But here it's really like an equivalence. So torsion-free one-relator groups embed into division rings. So this is a result of Lowen and Lowen from 78. Okay.
One question about that statement.
Sure.
Does it depend? Do you want the discrete group for any possible embedding or for a specific?
Any embedding. There's no. Yeah, it doesn't have to be the L ring, or it doesn't have to be strongly Hughes free or anything. It's just an embedding into a division ring.
It says that the group for one D is group for I mean, if the
D, right. Yes. Yeah. Yes.
So if you have
My handwriting.
that is finite, then you have
Yes. One division ring over where the dimension over the division ring as a D module is finite. Yeah, it does matter. Yeah. I mean, the point is that if you have cohomological dimension 2, then any projective resolution of length 1 will extend to something of length 2, and that'll be it. That's your whole resolution, and you can use that to show this. But yeah, I mean, maybe there's still something to be said, but the proof of this really does rely on the fact that you're cohomological dimension 2. Okay.
Are you assuming the group ring of a torsion-free dimension?
Yes, group ring of a torsion-free one-relator group. But yeah, I think they do it for general. It doesn't have to be ZG. I think they do it also for any. I don't remember the exact hypothesis, but maybe any group ring. Sam, do you remember this?
Yeah, any R can be any division ring.
Any division ring.
Be like twisted group rings as well.
Okay. But Q contains Z, so if Q, Q embeds and so does ZG. Okay, and another result which is very relevant. So local indicable groups, which I mentioned earlier, but maybe I didn't define. So these are just groups such that every finally generated subgroup, which is not trivial, surjects onto Z. So, okay, local indicable groups also embed. Okay, maybe I'll just add finally generated, but I'm not sure it's needed. Finally generated locally indicable groups, and this is right. Here's the long list of hyphens. Jaikin-Zapirain. Okay, this is one person, longer, and Lopez accent is this way. Alvarez. No? Oh, I wrote it wrong then. Okay. Thank you. Huh? Wait. No E?
A whole bunch everywhere.
We can spell without the accent.
Okay, no accents. Yeah. Okay.
And that's one person too.
This is one person. Yeah. So very long dash. This is two people, but they have the same surname.
So actually, as the theorem is fairly old, is a consequence of the result, or they were really addressing one-relator groups?
They were really addressing one-relator groups. So they show, Kaplansky's zero-divisor conjecture is true because you just embed it into a division ring, so there are no zero divisors. Yeah, this was the main result. Yeah, but okay, good point. The second thing. Result is just a consequence of a different result. So the result is that locally indicable groups satisfy strong Atelier conjecture, but I won't get into that story. But I will say this. So conjecturally, all torsion-free groups. Let's write this out. Torsion-free groups embed, or their group rings rather, embed into division rings. But I can't tell you how wildly true or wildly false this conjecture is. But people conjecture. Okay, so this is not, other than the common dimension, this is not a priori a big restriction. Yeah.
Wait, when you say do you mean there is a specific division ring for each group to embed into, or take a fake the division ring any single group?
Yeah, I mean, there's. Do you mean like you want to give me one ring and everything embeds into it, or yeah, I should have made that joke. That's great.
A specific division ring.
Into some division ring. I mean, usually the conjecture is embeds into a division ring with very nice properties. But yeah, for the purpose of this talk, is just any division ring will do. Yeah.
Open for left orderable.
Good question. I think it's open left orderable. Yeah. Okay. Confirmed. Yeah, I think it was also open. Yeah. No. Yeah.
Can the division ring be the original ring?
No. I think never. The division ring will never be the original group ring.
No.
Right? Not even if it's abelian, right? Like just never. Yeah. Yeah. There's no. Yeah. You need to find something. Sorry?
Not many units in a group unit.
Yeah, exactly. Yeah, that's big open problem. Right. Okay, so we have the criterion and we have a reason why it's useful. And let's finish the proof. So what do? Let's say we have X has non-positive mergens. It's just any two complex which has non-positive mergens. Okay, maybe I should say everything I'm considering here is is finite or locally finite, but yeah, we care about finally presented groups, so let's just say it's finite. And take H some finally generated subgroup. Okay, then using some ideas from Lauder and Wilton's papers, what do? We do some folding. We approximate this subgroup by sort of immersions of bigger and bigger two complexes. So we may start, let's say, with y0, which could just be a graph, which maps onto the generating set for h. Okay, and this is x down here. Then we want to progressively add more relations to this. You can consider just a presentation. So take a two-cell, which whose boundary map here is a relation in the group H, right? And well, there's going to be a disk diagram in X with that, which is, has that sort of boundary. And you just glue it onto y0 and fold. Gives you y1. And this will also immerse into X. And you repeat this. And these all factor through the cover of X whose fundamental group is precisely H. Okay, I'm going to draw a really long immersion error. There we go. Okay, and the direct limit of the fundamental groups of these guys is going to be precisely H. And we know that the Euler characteristic of each yi is always at most 0. I mean, if anything was trivial, then we'd be in trouble. Or rather, H would just be trivial, so we're done. So yeah, okay, assume H is non-trivial. So the Euler characteristic will always be 0 because X has non-positive immersions. And all these guys are aspherical, so we can compute homology. Sorry? You can take it to be any two complex such that this immersion factors through, let's just say it's the graph. Maybe you take a rose and you say each petal maps to a generator of H, which is finally generated, and then you fold that. So then it'll just be an immersion of a graph into X, such that the image on pi1 is precisely H. But naturally, the map on pi1 is not going to be injected, right? Unless you start off with a free group. So and the idea is to sort of make this as injective as possible as you iteratively fold things.
Why is the directive? I mean, it's a union of all.
Yeah, it's a union of, well, yeah, I mean, they're not necessarily inclusions, but yeah. Yeah. Yeah, that is very true. Yeah, I wish they were, but okay. Okay, so we have this, and then you just compute homology. So show that, well, whatever division ring you embed your group ring into, which by this wonderful theorem you can, because the fundamental group of X is locally indicable. And in particular, so all these guys. But anyway, so the d dimension of H2 of H is less than or equal to the d dimension of H1 of H. H was finally generated, so this is going to be has a finite dimension, and therefore so will the left-hand side. And then we can use the criterion from before and show that every finally generated subgroup has type FP2. And yeah, incidentally, if you choose this ring to be the right division ring, then this is second L2 Betti number of H. So this is the only thing I'm going to say about L2 Betti numbers. So we also have this. If disclaimer, if D is like, okay, some special division ring. Okay, so that's the second part of the recipe. How long do I have? 10, 15, 7 minutes. Okay, I'll be quick. Well, I'll be precisely 7 minutes quick. Final step, step 3. We have homological coherence, but it's not quite coherence. The final step will be hierarchies. Okay, I won't go into detail of the proof of the next result. Say some words. So we have groups homologically coherent, but we don't have, maybe they're not hyperbolic, so we don't know if they're coherent or not. So we need some extra tool, and the tool we show is the following. So this is in our paper, actually, which appeared on the archive today. So if G, now G is just any group, no restriction at all. So if G acts on a tree T, so okay, it's a tree with coherent vertex stabilizers, then homological, well, okay. Yeah, no, this is the previous step. So G is finitely presented if and only if G has type FP2. Now, I'm sure this was probably known to Dunwoody 40 years ago, but it's not anywhere. And yeah, so this is the main missing step to prove coherence of one-related groups. So as a sort of corollary of this, any group which has a hierarchy of any sort, so built up from amalgamated free products, H-line extensions, maybe you can pass to finite index subgroups from any set of groups which are coherent, that's like free groups, then you know that the coherence property is equivalent to the homological coherence property. Okay. Yes?
For the inequality, so for the phi one of the y case, in terms of for the left
Sorry, I missed the.
I'm just wondering how you put this. You put it for the phi one of the y case.
Yes. No analysis at all. I mean, maybe forget that I said this. Just they're all division rings, modules over division rings, and yeah, it's simpler than that. This is just a remark. Yeah, maybe that doesn't answer your question. Well, I guess it does, but maybe not satisfactory. Okay. Okay, so this is the final step. Now we just need an old theorem of Magnus, or a rephrasing of an old theorem of Magnus from 1930, when he proved the Freiheitssatz. So what he showed essentially was if G is one relator, there is a sequence of subgroups, Gn, blah, 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 G1, G0, which is just G. And these are all going to be one relator subgroups, but this is not, doesn't matter so much, such that Gi is a H-line extension over plus one over the next one related group. So H-line extension. Yeah, you need to terminate somewhere. So Gn is going to be a free group, free product, some finite cyclic group. That should not be 2, n. This is free, and n can be 1. So it could also be a free group.
Gi plus 1.
This is supposed to be the bonding map.
Oh,
Yeah, sorry. Yeah, it's a H-line extension where psi identifies 2 subgroups. Okay, well, maybe it should be plus 1. Okay. Okay. So maybe conclude, we'll just put 2 and 2 together. So applying the various results I've mentioned, this implies one-related groups are clear. Okay. I think I'll stop there. Yeah.
For the inequality between the 2 homologies, do you need to pick D to be like the right division ring? No.
No.
So how come, can you use the Lewin division ring then to?
We just need a division ring, and we know it exists by Lewin, and more generally for locally indicable groups by Jaikin and Lopez.
In theory, you don't require H stabilizers to be finitely generated, or it's automatically like almost non finite resolvability.
Yeah, nothing needs to be. Yeah, okay. Sorry, I forgot to add finally generated, but I guess it's here. So yeah, okay. Yeah, there's nothing needed. The edge stabilizers, vertex stabilizers can be infinitely generated. It doesn't matter. If G is finally presented, then you have this, and if you have FP2 over Z, then you have finite presentability. Yeah, I mean, yeah, the idea is you want to take some suitable refinements of your tree T. Yeah. Sorry. And throughout the proof, one shows that there is some tree on which G, if you're of type FP2 over Z, you act on with finally generated vertex and finally generated edge stabilizers. And then from the coherence of the vertex stabilizers, you conclude that your group was actually finally presented.
There's another question. So this is really Magnus or one-relator? I mean, Magnus is more complicated.
Yeah. So okay, you caught me. But HN extensions were not defined for like another 30 years. But yeah, one can extract this essentially from his original proof. I mean, because what he does is he just takes a map to Z of a one-related group and says the kernel is like an infinite amalgamated free product of one-related subgroups. But this is just essentially HN extension. So yeah, then I think it took 30, 40 years until Moldovansky, well, I mean, obviously after they were defined, Moldovansky observed that actually he was talking about HN extensions all along. Yeah. Yeah, it's also known as the Magnus-Moldovansky hierarchy.
Well, I have an old conjecture about complexes with non-positive emergence, that they all have, the groups all have hierarchies. For negative emergence, that they all have quasi-convex hierarchies, which suddenly it becomes useful instead of interesting. For negative emergence, it was useful because then we get more stuffness. For non-positive emergence, you have your coherence in that.
Yes.
I asked Gromov about this, and I bravely went to meet him, and he said, "Oh, you're already half there because you have a cyclic quotient already. So you already half there." I have not been able to push that through, but it's like if you believe in conspiracy, that's the next thing on the menu for all of us to see that happen. To be very excited. There'll be nothing left to do.
I have tried, and it's hard. Okay. Yeah, that's the next step. Yeah, but maybe we should hold off so we don't finish everything.
I heard this somewhere. Maybe I'm not getting the statement right, but I heard that if a group acts freely on an R tree, then it's coherent. And that Shalin proved this and maybe never published it.
Okay.
I mean, I was just wondering if there's any relationship with.
I'm not aware of that result, but yeah.
If you substitute coherence with higher coherence there and finally presented with Fn and everything, is that a theorem also? Or?
It's not a written down theorem, but I haven't thought about it enough. But yeah.
So there's nothing specific about dimension two.
No. Not well. I mean, there is, but it probably can be generalized. Just the focus was cohomological dimension 2. So everything above that is just there's nothing. But yeah, there's probably something to look at there.
This FP2 thing, is that like Dunwoodie's almost finally presented?
Well, so I think almost finally presented is FP2 over Z mod 2Z. Right?
Yeah.
So it's slightly, well, FP2 over Z implies FP2 over Z mod 2Z, but the other direction is not true.
Right. But basically, I mean, you use Dunwoodie's tracks, I guess, right?
So, like what an intermediate result does go via Dunwoodie's tracks. So that's like step part 2 or part 1 of the result. You have something of type FP2 over Z. Then there's like a short exact sequence. Okay, G is FP2 over Z, H is finally presented, and P is a perfect group. Now you do Dunwoodie's tracks with H to get a nice refinement of your H tree, because T is naturally an H tree by this homomorphism. And then the fact that this is perfect, acts on a tree, you can sort of get some, use the fact that free groups acting on groups acting freely on trees are free. And so, yeah, that's the idea. But yeah, we rely on it, definitely.
All right, let's leave other questions to the end.